Alright, hello and welcome back to mathematics. In this video we'll give you a brief revision rundown of sequences and series. We'll just go through the script and that should give you an idea of what we did in class. So we started with some easy examples of what a sequence is, recognizing patterns like, for instance, here that you realize, okay, this is always plus 2, and this is generally the first step that you're able to recognize patterns in sequences, and then this leads us to a description of said sequence. So for instance, here for this sequence here, we can give the nth element of the sequence directly. What this means is that here you just continue with you'd continue with, well, 11, then 13 and so forth, and then the question is, hey, if I am at the location n, then what is the value of this element? And here you easily see that, okay, you started 1 and then you always add 2. And how many times do you add 2? Well, here you have to be a little bit careful. For instance, here make an example. If you have the first, second, third, fourth element, maybe from the first to the fourth element you add 2 thrice, and so forth. For the seventh element you add 2 6 times. So you always add it 1 fewer times than the element position you want to be at. So here for the nth element we just added n minus 1 times. We dub this notation wise an. Note that here the n is in the subscript, so this is not on the same level. And as such, for instance, this one here would be a1, this one here would be a2, and so forth. Often you then describe a sequence with, in brackets, an, like this, and that is the whole sequence at once if you use brackets. But the most important is that you're able to label the elements a1, a2, an and know what they mean. It's not always that easy describing the general element or the element at the nth position. So for instance, here with the Fibonacci sequence we saw that, well, here you have to use the 2 previous elements to get the next one. So 1 plus 1 is 2, 2 plus 1 equals 3, 2 plus 3 equals 5, and so forth. So here, rather than saying, hey, I directly go for the nth element, it's easier for the moment to describe the sequence in another way and just say, hey, for the nth element, what I do is I take my 2 previous elements, an minus 2 and an minus 1, and add them up. Now, we realized in class that this is not enough to describe the sequence, because where would you start? Like, if you want to start now with actually giving elements of that sequence, you could start at 2 and 4 as a1 and a2 or anything. So we actually have to say that our first element is 1 and our second element is 1 as well. This here is not the same description or type of description as this one here. Note the key difference here. We used a formula in just n to describe an, whereas here we used elements from before, an minus 1 and an minus 2, to describe the next element, an. And This here marks also the sort of general difference between the descriptions you can have for a sequence. You can have a so-called explicit definition. That would be the example here. Or you can have a recursive definition. That would be the example here. And there are pros and cons for each definition. In the exercises we often use this one here a little bit more heavily, you've realized, but this one here, for instance, for the Fibonacci sequence is very easy to write down. A general description or explicit definition for the Fibonacci sequence is quite a little bit harder to find. Then you see that the general description often is not that easy in the sense of, yes, sometimes you have easy patterns, like for instance here you just have always times 2, very easy. Then here, this one here is maybe a little bit more difficult, but you should recognize these numbers as the square numbers. So this here is 1 squared, this here is 2 squared, 9 is 3 squared, and so forth. And then this would lead you here to the description, general description, Bn is just n squared. And here for 1, it would be, you start with 1, then you do 2 to the power of n minus 1 again, because you multiply by 2n minus 1 times. So there are various exercises to practice this for the explicit and recursive definition, and it just takes practice. So use the exercises from the red booklet to practice that as well as possible. Here you have another example with 3, 9, 27 and so forth. Again, here it's times 3 structure wise, and that leads you to the explicit definition of an is 3 to the power of n here, and the recursive one, an is 3 times an minus 1, and a1 is 3. So you always have to give a sort of an anchor point for a recursive definition. Then we focused on 2 particular structures that we've already mentioned now in the previous exercises. The first one is where you always add the same thing, so you always do plus 2 here, for instance, plus 2, plus 2, and here we already saw the explicit definition is an is 2n minus 1, or a recursive definition would be a1 is 1 and an is just the previous one plus 2, so an minus 1 plus 2. So this is what we call an arithmetic sequence. If we always add the same real number d, then we have an arithmetic sequence. Note that d can also be negative, of course. So even if we maybe here we did 1, then minus 1, minus 3, so we always do minus 2, then just d is equal to negative 2. In general, you can describe arithmetic sequences again recursively by saying an is just an minus 1 plus this difference d, and a1 is equal to some fixed number, let's call it c, where c is some fixed number in R, that would be the anchor. And then the explicit one, an is, now careful, that is the same pattern as before. You start at A1 and then you add the difference D, but if you want to land then at AN somewhere down the road here, you add the difference n minus 1 times. So here the formula was A1 plus n minus 1 times D. Then you can resolve various exercises together in class. For instance, this one here, A3 is 12 and D is 3. You want to describe it with an explicit and a recursive formula. So here if A3 is 12 and D is 3, you can go back twice. So you can go back by 6 and get that A1 is 6. And then you can just basically follow the formulas from above. So here, for instance, an explicit would be AN, we start at 6 plus n minus 1 times 3. And of course, if you want, you can do a little bit of algebra and say, okay, this is 6 plus 3n minus 3. So that's just 3 plus 3n. Looks a little bit nicer. Maybe the structure isn't apparent as here with the starting element and the n minus 1 jumps of plus 3. But it's algebraically a bit nicer. And then similarly, the recursive one would just be, well, you have to give the first element, A1 is 6. You could also give A3 is 12. That would be also okay. You just have to give some kind of anchor. And then, of course, AN is just AN minus 1 plus 3 here. Those in tandem are the recursive definition. Then, similarly, but just a different operation, we have so-called geometric sequences. Geometric sequence we've already seen would be this one here, where we always do times 3. So this here would be geometric because we always multiply with the same number and thus have a similar pattern to arithmetic, just with times instead of plus. And as before, note that of course you could also do always divide by 3, and then you would just phrase it as times 1/3. So here, similarly as before, you would just say the recursive definition is AN is AN minus 1 times Q, and again A1 is equal to some fixed real number. And then the explicit one, again, here is AN is equal to, you start at A1, then you always do times Q. And how many times do you do times Q? Well, n minus 1 times. And this accumulates, of course, in the exponent, now not with times, because if you do times Q, times Q, times Q, times Q, you summarize that as Q to the power of however many times you did times Q. All right, and then here you see, for instance, with the exercise, if you want to have A21 of this sequence, you can first set up the explicit formula, that is 1 times 3 to the power of n minus 1. And then you can just say, okay, now we calculate A21. That would be 1 times 3 to the power of 21 minus 1. So just 3 to the power of 20. Then we moved on from sequences. So previously sequence was just well, A1, A2, A3 and so forth, and then somewhere maybe our general element A1, but theoretically you could just go on and on and on. And now what we're basically doing we're moving from this as a sequence to, we just replace all the commas with plus, A2 plus A3 plus and so forth, plus AN. And again, here you could go on and on and on. We'll look at some even infinite sums later on. But if you stop at AN, we call this Sn, so the sum of the first n elements. And that you see here as well. Sn here is just A1 plus A2 plus A3 plus AN, so we stop at AN. Here we also talked about this notation, this capital Greek sigma notation. So here the sigma stands for sum, and the k below here is basically like a running index. It starts always at 1 or whatever number you put here, and then the convention that we have to follow is you always increase the counter by 1 and you stop summing up when you hit the number here. So here we say, okay, I plug in 1 for k, then I do plus and I increase the counter by 1, so that's A2, then I do plus and then I increase the counter by 1, land at 3 and so forth, and I stop at n here. So here, for instance, you have the following sums that you could write either in this sigma notation or write it down directly with the elements. So if you do A1 plus A2 plus A3 plus A4, you'd sum up the first 4 elements, and in the notation with the Greek sigma, you start at k equals 1 and you increase by 1 always and add, and you stop at 4. This notation or this sigma notation is often useful when you have a lot of elements that are summed up. You don't want to write a chain of 250 elements if you sum up 250 elements, but with that notation you can describe a sum of 250 elements very easily. All right, then we looked at the example of Gauss having to sum up the numbers between 1 and 100, and here we saw that there's a smarter way than just adding 1 plus 2 is 3 plus 3 is 6 and so forth. What we saw is that you can do pairs with 1 plus 100, 2 plus 99, 3 plus 98 and so forth. Think about what the last pair here is. Meanwhile, I'll jot down the result, which is of course always 101, and the last pair here is 50 plus 51, and then you've covered all the numbers between 1 and 100, because on the one side you go up from 1 and hit 50, and from the other side you drop down from 100 and hit 51, so in total you've summed up all the numbers. Alright, and then it's very easy to see, hey, how many pairs in total do I have? Well, I have 1, 2, 3, 4, 50 pairs, and that lands me at 50 times 101, and that's 5050. All right, and here to make the link to the general formula, we made it a little bit more sort of suggestive, in the sense of we had basically a sequence of 100 elements. So here, if I described this as, let's say, A1, A2 is 2, A3 is 3, and so forth, up until A100 is 100, then you could write this also as 100 divided by 2 times 1 plus 100. And here the 1 is our A1, our first element. The 100 is our A100, our last element. And this here, careful, this is not A100, this is how many elements you have. This is the n. And here, this, if you abstract this to a general formula, this lands you at the formula n times a1 plus an divided by 2 is Sn if the sequence is an arithmetic sequence. So be careful, that only works for arithmetic sequences. All right, then again we solved some examples here together. And here, for instance, you're given Sn is 136, and you have A1 is 3, the difference D is 4, so you directly know, hey, An is 3 plus n minus 1 times 4, and you know that Sn from the formula above is n times a1 plus an over 2. And if we want to find here the number of elements, this means we're basically looking for our n. And here what you can do, and that's often a very sort of classical trick that you saw in the exercises, that you say, I take this explicit formula for an and I plug it in here for an. And then what you get here is Sn is 136. N we don't know yet, but we know that A1 is 3, and we know that An is 3 plus n minus 1 times 4, so plus 4n minus 4 over 2. And then what you might already anticipate here, 6 minus 4 is 2, so in total what you get here is n times 2 plus 4n over 2, and that is still equal to 136. So here, if you divide this here by 2, you can even go as far as n times 1 plus 2n. Careful with the brackets, and then this is equal to 136, and here you'd just solve the quadratic with polysolve or some other way. All right, and similarly to arithmetic sequences, you can also, of course, have a series. You can also have geometric series. So here it's just the same thing. Now our sequence that we sum up is just a geometric one. So here Sn basically would be an A1 plus an A1 times Q is the second element, plus A1 times Q squared, plus, and so forth. And then the nth element, we saw that is A1 times Q to the power of n minus 1. And here we proved the formula in class together as well. I won't go through all the details here. The idea was just that you do Q times Sn, that will be A1 times Q plus A1 times Q squared, plus and so forth. And the last one then is A1 times Q to the power of n, and you compare it to your Sn. Your Sn is just A1 plus A1 times Q plus plus a1 times q to the power of n minus 1. And then what you do is you subtract basically q times Sn minus Sn, and then you see a lot of stuff cancels here. So this here cancels, this here would be here, cancels as well. Basically everything cancels except for this one here is left over. I don't have this one here, and this one here is left over as well. So you get a1 times q to the power of n minus a1. And then you can factor out the Sn on the left and divide by q minus 1, and then you get the formula here. So the general formula for summing up n elements of a geometric sequence is this one here, a1 times 1 minus q to the power of n over 1 minus q. Alright, and then you have these combined sort of exercises again. For instance, here you see q would be 3, a1 would be 2, and here an is 4,374. And then again find the number of elements here that requires us to determine n again, and here I'll leave you to solve that, or we solve that together in class. Here what I'll just mention is that if you go for the n, you have an is 4,374, and that is equal to a1 is 2 times q is 3 to the power of n minus 1. And if you solve that here, if you divide that by 2, you get 2,150, 185, 2,187, I hope that's correct, is 3 to the power of n minus 1. And here note that you need a logarithm to solve that. So here you'll get log 3 of 2187 is equal to n minus 1, and then you can solve for n and then just use the formula above. Okay, and then what we did next was to now actually address what if we just keep going with our sequence, as in what happens if we let n tend towards infinity. And here first we looked at different values for n, or rising values for n, and saw what different sequences here did in that exercises. And here we said, okay, the first one approaches 5 because 1 over n for rising values of n, that just gets smaller and smaller. So overall this just approaches 5. Here with this second one, we found that this approaches 1. So this here approaches 1. We'll talk about that in a moment. And here this one approaches infinity, or just grows arbitrarily large. And this one, the last one, this one here, it flip-flopped sort of, or flips back and forth, let's say, back and forth between 0 and 2. And those are some different behaviors that you can have for a sequence if you just let it go, or let n go towards infinity, and sort of approach and investigate the pattern for the sequence going towards infinity. And we looked at these 3 different cases based on these examples. So here it approaches a fixed number, so that would be case 1 here. Or it grows arbitrarily large, either with a positive or negative sign. So this would be the second case here. Or it does something else entirely. So there are pretty wild behaviors you could have for a sequence. And then we just summarize that as case 3. The notions that you have to know here was that in case 1, this here is called a convergent, because you approach a fixed number, and this here is called divergent. So whenever we talk of a convergent sequence, then this sequence approaches some fixed number. When we talk of a divergent sequence, it doesn't do that. Could approach infinity, could approach negative infinity, could flick back and forth between 2 or multiple values. That depends on the case, but in any case, you would still call this divergent. All right, and if those limits exist and you have a convergent sequence, what we write here is we write the name of the sequence here, and we stick this lim for limes or limit in front, and we say we want the limit of n going towards infinity. So we're interested what happens if n grows larger and larger. And then we say an approaches a limit L, or more mathematically, the limit of n towards infinity of an is equal to L. For convergent sequences an and bn, this limit has some nice properties. For one, it distributes over plus and minus. It even distributes over times, and it distributes over quotients. So you can take apart the limit into two parts, in the sense of you can put the limit here and put the limit here. If the limit of bn is not equal to 0, of course, otherwise you would divide by 0. And careful, here an and bn must be convergent. So here is a example where one would now naively maybe think, hey, I want the limit of this whole thing. And now I was just told that I can take the limit of something divided by something. I just take the limit of the upper part and the limit of the lower part, divide the results by each other, and then we're fine. Well, look at that exactly here. We saw that this one here, for larger and larger values of n, this as a sequence is not convergent because it approaches infinity. Same thing with this one here. So as it stands at the moment, neither of those two are convergent, but we can use a little trick to make them convergent. And here what we do, we look at the largest exponent of n, and we say, okay, I'm going to simplify this fraction with n squared here and here. And then my an looks a little bit differently. So now if I just divide by n squared on top and bottom, I do that piecewise for each part of the sum, and then I get 2n squared by n squared is 2, plus 3 by n, 3n by n squared is 3 by n, minus 3 by n squared. And then similarly on the bottom, I get 3 minus 5 by n plus 7 by n squared. All right, now the cool thing about that is if I now pull this apart a little bit and then take the limit of n towards infinity of an, so that would be the limit of n towards infinity of this whole thing. And now what you see here, now we have actually the case where individual parts approach a fixed number. Namely, this is just 2, so there's no n in it, so it just stays 2. This here approaches 0, this here approaches 0, so those all approach 0. This here approaches 0, this here approaches 0. So I actually, I'm not going to write it out, but I can take this lim n towards infinity to each of those 3 parts on top and bottom, and then just take the limit individually. And what I get here is 2, well, plus 0 minus 0 over 3 minus 0 plus 0, and that's just 2/3. So here the limit is just 2/3. And whenever you have a quotient or a multiplication or even an addition or something, you want to break it down into smaller sequences. The problem is those smaller sequences here, they individually have to be convergent for you to exploit those properties of the limit. And that means that you might have to use algebraic tricks like this. All right, then we briefly looked what convergent actually means mathematically, and here we plotted the sequence of 4 minus 1 over n, and here if you plot that with n on the horizontal axis and the value an on the vertical axis, you get that for 1, I plug that in, 4 minus 1 over 1, that would be 3. So here I get, if this is maybe 3, let me put that down a little, 3 here, and then here maybe I have 4. So here the first element would be 3, the second element is 4 minus 1/2, so that's 3.5. The third element is, well, 3.75 and so forth. Here the elements get harder and harder to accurately sort of plug in, but what you see here, of course, 4 is going to be a threshold that is never touched or crossed, and it's also the limit, of course, because here 4 minus 1 over n approaches 0. So with our intuitive notion from before, we already know that 4 is the limit. But mathematically, what actually happens is that you say, okay, I'm gonna put sort of a band around this limit, or what we think is the limit. And this is the so-called epsilon band or epsilon band. That you see, okay, here I go epsilon down, and here I go epsilon up, and then you sort of have a band of 1 epsilon in each direction. And the notion, or when 4 actually is the limit of the sequence, is whenever you can make this epsilon band arbitrarily small, and no matter how small you make it, there is a threshold where from some element onwards all the other elements then are contained within the epsilon band, then the limit exists and it is equal to L. And here in our example, L here would be 4, and an would be this one here. And then you say, okay, if there exists some fixed number n epsilon such that for all elements an with n larger than n epsilon, those are in the epsilon band. So that's just the absolute value of the distance between the element and the limit, smaller than epsilon. And if that is true, then L is the limit of the sequence an. So here, for instance, for my specific epsilon band, I don't know, maybe here this would still just be outside the epsilon band, and then from here on, from 4, all the next elements are in the epsilon band. So here, this 4 here, for instance, would be n epsilon. All right, then we turned to limits of specific series and more specifically geometric series. And we saw that for a finite series you can talk about the sum, but in any case you break off at some element an. And now what we want to do here is we want to look at infinite series and say, okay, here we continue with more and more elements, and maybe the sum of that infinite series, or the result of that infinite series, is a fixed number as well. So that would be then the limit of sum. Conceptually, what we're doing nothing else than we just take the partial sums. So S1 is just A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and so forth. And we see if this sequence converges. So the limit of a series is actually just the limit of the partial sums. What we looked at here was examples like, for instance, A1 0.9, A2 0.09, A3 0.009, and so forth. And here, if you write that as a sum, 0.9 plus 0.09 plus 0.009 plus, and so forth. You might already recognize, if you sum that up, this is actually 0.9 infinity, and here the limit is 1, because 0.9 infinity is the same as 1. Why? Well, we're going to give an argument in a moment using a geometric series. One classical argument is that you say, okay, if 0.9 is x and I don't know what it is at the moment, I can just look at 10 times that. 10 times that would be 9.9 infinity, and this here would be 10x. And then I can say, okay, I do the 10x minus the x, so I get 9x is equal to 9.9 infinity minus 0.9 infinity. Well, that's just 9, so 9x is 9, and then x is equal to 1. That's one way to how to figure out the limit here, or argue that the limit and 0.9 infinity thus is 1. Another argument is that you say, okay, 0.9 plus 0.09 plus 0.009 plus, that fits into the framework of a geometric sequence or series here with times 1 over 10 as q. So here q is 1 over 10 and a1 here is 0.9. So we can analyze the series of a geometric sequence, and in the chapters before we said, okay, the formula for the n first elements summed up of a geometric sequence is this one here. And now I can say, okay, now I take my limit to the different things. Here 1 is not interesting, stays 1, 1 is not interesting, stays 1, q stays q, because there's no n in it. The only interesting thing is this one here. And the limit of n towards infinity of q to the power of n, well, that of course depends on the number q. And if you think about it a little bit, and we discussed that in the lesson, q to the power of n, that converges only for certain values of q. Namely, it only converges for q strictly in between -1 and 1. And in that case, you have limit of q to the power of n is equal to 0. Because if you take successive powers of a number in between -1 and 1, you'll approach 0. All right, if you plug that in and you say, okay, this thing here, this is actually 0, what you're left with is this formula here. And that's the formula for an infinite geometric series. So this formula holds if, and only if, of course, q is in between -1 and 1. All right, well, let's test that here. If we use the formula here, which is a1 over 1 minus q, well, I have a1 is 0.9, I have q is 1 over 10, so 1 minus 1 over 10, or 0.1, well, that's just 0.9. So then I have 0.9 over 0.9, and that's equal to 1. So that's the nature of infinite geometric series, and they always, or this always revolves around this formula here. So with that in mind, you can calculate all kinds of infinite geometric series. You can also do neat little tricks like rewriting decimals that are periodic as fractions. On the one hand, here you can use the same trick as before. So here what I do with 0.131313, so 0.13 periodic, is I want to take the whole thing that is periodic to the front. So on the left hand side of the decimal point. And here what you might notice, well, if I write that down, what I have to do is I have to calculate times 100. So if this is x here and this is 100x, I can do the same trick as before. I do 100x minus x, that's 99x. And then I do 13.13 periodic minus 0.13 periodic. Well, that's just 13. And then x is just 13 by 99. And if that seems shady to you, you can maybe use a calculator to convince yourself that if you plug in 13 by 99, it actually is equal to 0.13 periodic. Or you can also say, okay, 0.13 periodic is equal to 0.13 plus 0.0013 and so forth. The next one would be, well, 0.0000013 and so on. And then you see, okay, now I have the framework of a geometric series again. And here Q is 1 over 100. So I do times 1 over 100. And here A1 is 0.13. And if you calculate that, then here the limit of n towards infinity of Sn is equal to A1 0.13 divided by 1 minus Q. That's 1 minus 1 over 100, so that's 0.13 divided by 1 minus 100 is just 99 hundredth. And then here, careful, double fractions, so that's 0.13 times 100 by 99, and 0.13 times 100, well, that's just 13. So that is, this is sort of the, I don't know, sort of the quick and dirty trick. And the other one is the maybe a little bit more elaborate, but fitting into the framework of geometric series or infinite geometric series. All right, and then that's just about everything from the sequences and series script. As always, this is just a very top level input or summary of the whole thing. So do use the exercises in the red booklet here to practice those things, because there are a lot of different exercise types and so forth that I now, of course, didn't explicitly mention.